last couple of lectures we looked at reduced binary quadratic forms. We proved that there of any given negative discriminant there are at most finitely many reduced binary quadratic form of that discriminant, and any equivalence class contains exactly one reduced binary quadratic form. So, if you want to find out all the equivalence classes of binary quadratic positive definite binary quadratic forms of a given discriminant, you just have to list down all the reduced binary quadratic forms of that discriminant, and there is a very simple algorithm to do that. You have a strong restriction on A that gives you a restriction on B and C as well, and so you just go through a finite list and you get all reduced binary quadratic forms of a given discriminant. Then we started, so this was all the study of binary quadratic forms. How does that relate to our main topic of this course, which is about algebraic number fields? So, we started by relating binary quadratic forms to quadratic fields, and so we will continue this. So, let me recall what we were doing. Okay. So, let K be an imaginary quadratic field Okay, so it is a quadratic extension of Q obtained by adjoining square root of a negative rational number. Okay. So, we are going to relate ideals of K. So, our goal today is to relate ideal classes in K to equivalence classes of binary quadratic forms. Okay. And so, how do we do this? To do this we do the following. Right. So, what I am going to do first is, so okay. So, let us start. Let A contained in OK be a non-zero ideal. Okay. So, it is a finite index subgroup of OK, right, and so we know that OK, the index of this is norm of A, right. This is, we know this, and this is less than infinity, right. So, A is a free Z module of rank 2. Right. So, we fix a basis alpha 1 alpha 2, fix a Z basis alpha 1 alpha 2 of A, right. What this means is A is alpha 1 Z plus alpha 2 Z, okay. That is what this means. And so, what we are going to do first depends on the choice of basis, but eventually we will show that things are independent of choice of basis. So, let alpha be an element of A, then we can write alpha as x alpha 1 plus y alpha 2. And what we did last time is we took norm of alpha, right. So, let us say that the Galois group of K over Q is 1 and sigma, right. It is a quadratic extension, and so it is Galois with Galois group isomorphic to Z mod 2Z, cyclic group of order 2. And so, I can take sigma to be its non-trivial generator. So, norm of alpha is alpha times sigma alpha, but I can write this as x1 alpha 1 plus y, sorry, not x1, x alpha 1 in my notation, x alpha 1 plus y alpha 2 sigma x alpha 1 plus y alpha 2. So, where are these x and y? They live inside z, right. So, sigma fixes x and y, does not do anything to x and y, and it acts on alpha 1 and it acts on alpha 2, right. So, I am just doing the usual manipulation. If I multiply this out, I get alpha 1 sigma alpha 1 plus x y times alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, right, plus y squared times alpha 2 sigma alpha 2. Now, notice that alpha 1 sigma alpha 1, alpha 2 sigma alpha 2 and alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, they are all in Z, right, as they are fixed by sigma. Anything in K that is fixed by sigma will be contained in Q, and if we start with algebraic integers, it will be contained in Z, right. And so, we get a, so norm of alpha, so norm of alpha you can write it as right. So, norm of alpha, this is, let me denote it by a1 x squared plus b1 xy plus c1 y squared for a1, b1 and c1 inside Z. Right. So, it looks like a binary quadratic form, except that this is not the binary quadratic form that we associate with A yet. Right. So, what I am going to do is the following. Right. Okay. So, what we are going to do is the following. So, notice, so here are some observations. We have proven earlier, so we have seen earlier that A times sigma A, this is the ideal generated by norm of A, right. This is the ideal generated by norm of A inside of Z, okay. And if we look at determinant of alpha 1, alpha 2, sigma alpha 1, sigma alpha 2 square, then this thing is equal to norm of A squared times the discriminant. So, this is the discriminant, right. Yeah. Okay. So, what I am going to do next is yes. Yeah. Okay. So, what I am going to do next is the following. So, instead of considering this thing, what I am going to do is I am going to consider norm of alpha divided by norm of A, right. So, this thing will give me A x squared plus b x y plus c y squared. And so, what are these A? A is A1 by norm of A, B is B1 by norm of A, and C is C1 by norm of A. And but why are all these things inside Z? So, my claim is that A, B and C are still in Z, and what is the reason for this? Well, the reason for this is quite simple. You see, norm of A, as we recalled on the earlier thing, it's inside this, right. So norm of A as an ideal is this. Now, alpha 1 sigma alpha 1, this thing is in here, alpha 2 sigma alpha 2 is in here. But what is product of two ideals? Product of two ideals is you take product of all possible elements in it. So, first one from the first, second one from the second, and then you take sum of all these things. So, alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, this is also inside this, right. Hence, norm of A divides A1, B1 and C1, okay. Hence, A, B and C is in Z, right. So, that is the reason why it is in Z. And now, the second claim is that discriminant of ax square plus bxy plus cy square is dk, right. So, that is my second claim. Okay, how do I show that? Well, what is the discriminant here? Discriminant is b square minus 4 times ac. And what is this? Sorry, what is this thing? Well, this is b1 square divided by norm of a squared minus 4 a1 c1 divided by norm of a square, right. So, that is what it is. So, this is b1 squared minus 4 a1 c1 by norm of a squared. Okay. So, we want to find out what the discriminant of what is b1 square minus 4 a1 c1, and to do that we go back to our definition of what so to do that, what we are going to, so what was A1? A1 was alpha 1 sigma alpha 1, B1 was alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, and C1 was alpha 2 sigma alpha 2. Right. So, if I look at B1 minus 4 A1 C1, then this thing is simply alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1 squared minus 4 times alpha 1 sigma alpha 1 alpha 2 sigma alpha 2, right. So, if you rewrite the whole thing, you get alpha 1 sigma alpha 2 minus alpha 2 sigma alpha 1 squared, which is same as determinant of alpha 1 alpha 2 sigma alpha 1 sigma alpha 2 whole squared, which we know is norm of A squared times dk, right, because that is how the Z basis works. So, this comes from linear algebra over Z, and and so hence we have proved. So, hence discriminant of A x square plus b x y plus c y square is dk. Okay. All right. So, what we have, we have done the first step. So, what have we done up till now? So, what have we done up until now? So, given a non-zero ideal A of OK, we have attached a binary quadratic form ax square plus bxy plus cy square with discriminant dk. Okay. So, given an ideal, non-zero ideal, we have attached a binary quadratic form. So, now what happens, and this choice, so this depends, well, a priori at least it seems to depend, and it actually does depend, depends on the choice of a basis, a z basis of A. So, what happens if you choose a different z basis? So, what happens if we choose another z basis alpha 1 prime and alpha 2 prime for of A, okay, another z basis like this. So, what happens in that case? So, that is what we will find out. Well, first of all, we know that if we choose a z basis like this, then yeah, then there is a okay. So, let me write that down. So, if so then there exists a matrix A in GL2 of Z such that right, okay, yeah. So, such that yeah, how do I say this? Okay, such that we get, you know, it is a change of basis matrix, and so yeah, right. So, what I want to do is I want to say that yeah, or maybe I'll write it like this, obtained as follows. Then what we do is we consider a matrix obtained as follows. Right. So, you write alpha 1 prime as x 1 alpha 1 plus x 2 alpha 2, and you write alpha 2 prime as y 1 alpha 1 plus y 2 alpha 2, right. Then you write A to be x 1 x 1 x 2 y 1 y 2. So, this is the change of basis matrix from alpha 1 alpha 2 to alpha 1 prime alpha 2 prime. Okay. All right. And yeah, so if I take alpha as x alpha 1 plus y alpha 2, yeah, maybe I should have it the other way around. So, let me write it like this. Then you, yeah, so I am doing all these explicit computations for you now. So, this is x 1 alpha 1 plus x 2 alpha 2 plus y y 1 alpha 1 plus y 2 alpha 2. So, if I rewrite this whole thing in terms of alpha 1 alpha 2, then I get x 1 plus y 1 times alpha 1 plus x 2 plus y 2 times alpha 2, right. And so, if you yeah, so something that I had written as a in alpha 1 prime and alpha 2 prime basis, now I have written in terms of alpha 1 and alpha 2. Okay. And how do I obtain this? So, the way I obtain this is yeah, so the way I obtain this is x 1 plus y 1 and x2 plus y2. This is x1 y1 x2 y2 times x and y, right. Yeah. So, this is why this is the change of basis matrix, and now you see that yeah. So, let a1 sorry not a prime x square b prime xy plus c prime y square be the binary quadratic form associated with a using the basis alpha 1 prime and alpha 2 prime. Right. Then what happens here is yeah, I mean we know how these things are obtained. So, a prime is alpha 1 prime sigma alpha 1 prime by norm of a, right, and b prime is alpha 1 prime sigma alpha 2 prime plus alpha 2 prime sigma alpha 1 prime by norm of a, and then c prime again is alpha 2 prime sigma alpha 2 prime by norm of a, right. Yeah, but you see how these things are written. You can just rewrite them as, so a prime is yeah, x1 alpha 1 plus x2 alpha 2 x1 sigma alpha 1 plus x2 sigma alpha 2 by norm of a. So, I will just do this calculation for one of them, not all of them, but just one of them. So, this is x1 square right, yeah, okay. Let me, oops. Yeah, so if you multiply this out, you will find out that this is exactly a x1 square plus b x1 y1 plus c x2 square. Sorry, this should be x1 x2, not x1 y1. Okay. And similarly, you get a you get formulas for b prime and c prime using using this. Okay. Right. So what you have proven in effect, so hence we get that a x square plus b x y plus c y square, a prime x square plus b prime x y plus c prime y square are equivalent binary quadratic forms. This is not quite true because I have this in GL2Z, right. So, this is not, yeah, maybe this is not quite true, right, because my matrix A is in GL2Z. So, so not quite. So, this is what we want. This is not quite true as A belongs to GL2Z. We want A in SL2Z, right, that is what we did earlier. And so, there is a very easy way to fix this. So, fix, what is the fix for this? The fix for this is that you start with, and remember up to now we did not use anything about imaginary quadratic fields. So, everything I did up to now works for real quadratic fields as well. This is the first place where we use that we are working with imaginary quadratic fields, and it is very crucial. So, what we do is we what is called orient our basis alpha 1 alpha 2 such that such that the imaginary part of alpha 2 by alpha 1 is bigger than 0, right, it is positive. So, this is a convention that we always take, and so similarly alpha 1 prime and alpha 2 prime is such that the imaginary part of alpha 2 prime by alpha 1 prime is bigger than 0. It does not matter which order you take them in, as long as you are consistent with your order. You either take alpha 1 by alpha 2 or alpha 2 by alpha 1. This is the chosen order, alpha 2 by alpha 1, and you take its imaginary part to be this. Then A will actually be in SL2 of Z, right. So, this is the place where we crucially use that we are working over imaginary quadratic fields, and we do not have a way of doing this if we are working over real quadratic fields. So, that is an issue. In any case, so what have we done up to now? So, up to now, so start with we have attached an equivalence class of binary quadratic form of discriminant dk to any non-zero ideal A in OK, right. So, we started with a non-zero ideal, and now we have attached a equivalence class of binary quadratic form of discriminant dk, and this attachment does not depend on choice of basis, right, because if we change our basis z basis for A, we change our binary quadratic form by an equivalent binary quadratic form, right. So, that is why we are in the same equivalence class. Alright. So, the next thing that we are going to do next time is show that if we attach if we replace our A by an equivalent ideal class. So, remember, when are two ideal classes equivalent? When they differ by a principal ideal, right. So, if we replace A by alpha times A, where alpha is an element of K cross, then again we get an equivalent binary quadratic form. So, that is what we are going to show, which means that we would have shown that how to attach an equivalence class of binary quadratic forms to equivalence class of ideal classes, and then we will show that this attachment is actually a bijection. So, we get a 1-to-1 map from class group of K to binary quadratic forms. So, this is what we had started to what we had said in the beginning we would do. Okay. All right. So, that is all that we will do next time. Thank you.